Welcome everyone to the California Water Data Consortium's April Data for Lunch, When Rivers Run Hot, with aquatic ecologist Jonathan Walter. I'm Elisa Salinas-Centric, the Senior Communications and Outreach Manager at the Consortium, and I'll be moderating today's event. A couple housekeeping items before we begin. Yes, this meeting is being recorded and will be sent out via email and posted to our website and YouTube channel. Questions are welcome throughout the presentation. Please add them to the chat box. I know this says Q&A box, should say chat box, so that we can answer them at the end of the presentation. And then there will be a brief survey at the end of the event when you close your Zoom window. So this helps us plan for future Data for Lunch events and offerings. This is today's agenda. Jonathan's presentation will be about 30 minutes or so. Then we'll have a facilitated discussion where we've prepared a couple questions ahead of time for John. And additionally, he's graciously agreed to stay on Zoom for your questions in an informal discussion at around 1 p.m. Again, please feel free to pop your questions in the chat box of Zoom throughout today's event. I'll be collecting those for our discussion at the end of the presentation. I also have a couple of consortium staff on the call to help support and answer any kind of quick questions. Hannah's on the call, as well as Robin, Amanda, and Sonia as well. So a bit of background on the consortium. We are an independent nonprofit organization created by a partnership of state agencies and others to ensure California has access to the best possible water and ecological data. We believe this helps ensure that everyone living and working here can prosper in the face of unprecedented climate challenges. We do this by bringing together diverse partners, including water managers, state agencies, researchers, industries, and community organizations to improve how water and ecological data are shared, collected, and used across California. So I'm going to drop our website in the chat. You can peruse that at your leisure if you want to learn more. A little bit about our Data for Lunch series. It's one way we fulfill our mission, basically by providing a forum to learn about cutting edge water data technologies and research, share insights about water management challenges and solutions, connect water professionals across different sectors, and explore how better data can lead to better decisions for California's water future. If you want to learn more about our series, I will also drop that in the chat. Or if you're interested in actually presenting at one of these in the future, feel free to reach out. I'd also like to take a moment to thank our sponsor, the California Department of Water Resources, for making this Data for Lunch series possible. If you or your organization are interested in sponsoring future Data for Lunch events, please reach out to me directly for more information. I'm going to drop my email and the link to the sponsorship flyer in the chat. Oh, I'm going to redo that sponsorship flyer link since it didn't pop up. Oh, okay. Well,
I'll
you can
redo
copy
it.
and
Don't
paste
worry.
that. Thanks. And then I hope you all saw that we are hosting a summer roundtable event on June 3rd in Sacramento. Public registration just opened up this morning. I think many of you on the call received that or received a personal invitation from Robin. This year's theme is putting water data to work, maximizing the climate bond's impact, focusing on how data can help California make the most of Prop 4's $3.8 billion water resilience investment. We've assembled a really impressive lineup of speakers who are listed on the screen and more. And if you're interested in the intersection of water data and climate resilience, this is an event that you don't want to miss. We do expect to sell out pretty quickly, so there's a wait list available as well. And I'll drop the link to register in the chat here. If you have any trouble with registering, feel free to reach out via email. And finally, we hope you will join us for another Data for Lunch in a few weeks with Hannah Ake, who's on the call. And that will be on sharing data for drought resilience. You'll be able to discover how collaboration across state agencies, it improves water management in California. The talk will be featuring Ashley Bizek from Flow West and a team of environmental data scientists from UCSB's Friend School. With that in mind, I'm excited to welcome Jonathan Walter from UC Davis's Center for Watershed Sciences to our Data for Lunch today. Jonathan is an ecologist at UC Davis who specializes in using data science and mathematical modeling to tackle pressing challenges in California's rivers, streams, and aquatic ecosystems. Today, he'll share his research on how river heat waves are becoming more frequent and intense across the Western US, and what this means for California's water management strategies and ecosystems. I'm going to hand the reins over to Jonathan and stop sharing my screen. Thank you again, John, for sharing your work and research today. Obviously, this topic touches a lot of aspects of water management, so I just want to remind all the folks on the call that we encourage questions from all perspectives. So yeah, feel free to drop that in the chat.
Awesome. Thank you very much. And I especially want to thank the Data Consortium for this invitation. And I'll just add to the introduction that I'm relatively new to California. I moved here this past September. And so I'm really grateful for the platform to share my work with this audience. And knowing that I'd be speaking to many folks with really deep knowledge of California water really caused me to think deeply about some of the context and implications of this work. And I'm really excited to share that with you. So I think we've all experienced atmospheric heat waves, periods of prolonged hot temperatures, not just normal hot, but extreme hot that lasts for days. We want to camp inside in our air conditioning, and you might need to take special precautions if you need to be outdoors. There's also growing recognition that heat waves occur in aquatic habitats. The oceans, our estuaries, lakes, and of course, what I'm going to focus on today are streams and rivers. And one of the things that this highlights for me is that climate change is not just changes in averages, but also changes in the frequency and severity of extremes. And just as atmospheric heat waves can be physiologically stressful and even deadly for people and plants and animals living on land, they have major impacts on aquatic biota and ecosystems and the benefits that humans get from nature. This figure summarizes documented impacts of 30 or so major marine heat waves since the 1990s that happened across the globe. And the key at the bottom illustrates a range of different impacts, from reductions in yields from aquaculture and fisheries, harmful algal blooms, release of carbon dioxide in the atmosphere, spread of wildlife diseases, mass mortality of aquatic animals, and losses to tourism and recreation. And so one of the things that these impacts bring home for me is it's not only that nature that suffers during heat waves, but also our socioeconomic systems, so people's lives and livelihoods. And one of these events that will stand out for much of my California-based audience is the 2014 to 2016 warm blob in the Eastern Pacific Ocean, where every single one of these impacts has been documented. But all that said, much of what we know about aquatic heat waves and their impacts comes from studies of the coastal ocean and large lakes, with understanding of heat waves and rivers and streams lagging behind that. And since I'm a data scientist and this is data for lunch, I think I'm compelled to explain how this is partly a data problem. So for our oceans and large lakes, satellite remote sensing data, like you see in this example, facilitate really near constant wall-to-wall monitoring. But the spatial grain of these measurements, which are often things like 5 kilometers by 5 kilometers in pixels, that's really too coarse to separate streams and rivers, or smaller lakes for that matter, from the landscapes that they're embedded in. And so we rely on local measurements, mainly ones that are made using automated sensors deployed and maintained by people. And that creates some challenges for collecting data on many individual river segments, but also for sharing, finding, and accessing data that's collected by dozens, if not hundreds of researchers spread across many different organizations. And just to compare that briefly to satellite data, once a satellite is operational and there's a pipeline established for that data, it might just be a handful of people from one or a few organizations that are really hands-on with that to create usable data on some variable for any place that that satellite can see. So today, I want to talk mainly about two studies that represent some of the first regional to national scale studies of heat waves in streams and rivers in the US. By synthesizing long-term water temperature data, we're able to provide new insights on first, where and when riverine heat waves occur in the US and how this has changed over time. And second, on how and why riverine heat waves co-occur in time across the Western US and in local river networks. Of course, I can't take all of the credit or all of the blame for this work. And I want to particularly shout out Spencer Tassone. He's a common thread between these two projects and is the lead author on the first study that I'm going to share with you. Spencer did this work while he was a graduate student at the University of Virginia, which was also my previous stop. And he's now a scientist with the USGS. All right, so let's get down to business. All this research is underpinned by being able to quantify riverine heat waves using a robust and reproducible definition that indicates where and when they happen. But first and foremost, we need data. Specifically, we need long time series of daily water temperature. And in the two studies that I'm going to discuss, the exact sources and criteria for including a site are going to differ a bit. But in general, we're talking mainly about data provided by government agencies through the USGS and California DWR's CDEC data portals. And we're looking for time series of 15 or more years with nearly continuous daily data. Or data that are at a finer time interval, like hourly, that we can process into a daily mean. And I'll explain shortly why we need such long data. And near the end of my talk about some interesting, at least interesting to me, opportunities to relax that for the future. So probably somebody out there in the audience is thinking, oh, but there's a bunch of data in some other place. And that really highlights one of the challenges of this sort of research. The data are often fragmented across different databases, and it can be really time consuming to find, to access, to integrate those different data sets together. So we've done that in some limited ways here, but there are still opportunities to expand data access and make it more usable for research and for management initiatives as well. Once we have those data, this figure illustrates the process of detecting and quantifying aquatic heat waves. And this is borrowed from a well-established definition used in the study of marine heat waves. So our many years of data allow us to identify the long-term mean temperature that we'd expect for any place on any given day of the year. And that's the blue line. And we can also use those many years of data to identify a threshold for extreme heat on any given day of the year. And that's the green line. So we need a lot of data in the form of long time series, so we know what's normal and what's extreme for a given place and a given time of year. And in these studies, that green line corresponds to the 90th percentile of temperatures that have been observed in the recent past for that time of year. And when that threshold is exceeded for a short time, say a day or two, we would call that a heat spike. But when that threshold is exceeded for a more extended period, and in these studies, that's a period of at least 5 days, that's what we consider a heat wave. We consider it to end when temperatures drop back down below that threshold. And then when a heat wave is identified, we can extract information like how long it lasted and how intense it was based on how hot it got relative to normal conditions. And we do this on a site-by-site basis for however many locations we have suitable data. Before digging further into these studies, I want to step back a moment and just formalize an extremely, and I want to emphasize extremely simple set of controls on river temperatures that will be useful to keep in mind as we talk about these heat waves, how they develop and why. So rivers exchange heat with the atmosphere and can be warmed by incoming solar radiation. And they're also affected by flows. So water is going to flow in from upstream at some temperature, And then how much water is in the river also influences how easy it is for other processes to heat and cool the river. In this first study, which you can think of as a broad scale survey of patterns and trends in riverine heat wave occurrence, we used data from the USGS to collate stream temperature data for 70 different locations across the US, some of which had paired discharge data as well. This map shows the location of those sites, and this study focused on 25 years, beginning in 1996 and ending in 2021. I'll also point out these results have been published. This QR code that's on the next handful of slides will link you to it if you want to learn more. And that citation stub in the top right can also help to find it. Okay, so finally some results. So the plot that just popped up on the right shows the relative frequency of site and year combinations with a given number of heatwave events. That's on the x-axis, and how that varies across regions that are color-coded the same way as in the map. So in several regions, 1 to 3 heat waves per year are more common than none. And in some cases, there are as many as 12 unique heat wave events at a site in a year. And there also are some differences among these regions. So focusing on two where we have a lot of sites, a lot of data for, the Northeast, which is our kind of brick red color, and the Southeast in yellow, we see both a greater overall frequency of heat waves in the Southeast, as well as more extremes, with the most heat wave prone sites in the Southeast experiencing as many as 9 heat waves in a year, but only 6 in the Northeast. In terms of when heat waves occur, this pie chart shows that the number of riverine heat waves in our data set is about evenly distributed among the 4 seasons, though with a bit greater frequency in spring and summer. And this highlights something important about the way we define heat waves for this analysis. It's in comparison to what's normal for the time of year, not just a static, oh, 80 degrees Fahrenheit is too hot. Static thresholds can be useful when there's a clear, physiological target for a species of interest. In California, we do that with Chinook salmon. But instead here, we're trying to understand when and where it's anomalously warm compared to what's normal for the time of year. And this choice reflects the principle that there are many different organisms in any place. They have many different life histories, but that they're adapted to local conditions. And so if it's really warm for January, even if the absolute temperature would be quite cool for July, it's likely causing stress and possibly worse for organisms who are adapted to the temperatures that are normal for that time and place. We also, in this study, examine not just when heat waves are timed during the year, but some conditions under which they occur. And here we're looking at the distribution of river discharge during heat waves. So how much water is flowing through the river relative to the average, and this has been by month. And if it's been a while since you've looked at a box and whisker plot, the heavy horizontal line indicates the median. 75% of the data fall within a box. And so this shows us that possibly excluding our winter months, heat waves were more prevalent when discharge was below normal for that time of year. In that range of months that I've circled in red, those means or medians and the boxes indicating the 75% of the data distribution is all shifted to below zero, below normal. Another key takeaway from this study is that riverine heat waves have been become more prevalent over time. From 1996 to 2021, frequency increased by about 0.06 events per year, which doesn't sound like a lot, but compounded over time, this is associated with a doubling in the number of heat wave days per year since 1996. And there are some nuances here as well. Increases have been strongest during the summer and fall seasons, and increases have also been more rapid above reservoirs and in free-flowing rivers than below reservoirs. And I'll return to the importance of reservoirs and dams for heat waves a bit later on. But this is not entirely surprising, given how reservoirs and dams can decouple flows and water temperatures from natural patterns. But please don't quote me as saying dams are good for the ecology. But given that we do live in a world where they exist and help to meet the needs for people and agriculture, maybe there's some wins to be had. So we'll think a little bit more on that later. So previously, so we were looking at general site-by-site trends in heat waves. And this allowed us to uncover some new information on um, when and where river and heat waves occur and how that's changing over time. But one piece of the puzzle that that approach left out is how different streams and rivers are connected to each other, both directly via flows through river networks and indirectly through shared effects of climate. And so some ongoing research building on what you just saw investigates the co-occurrence or synchrony of river and heat waves. And understanding to what extent heat waves co-occur and reasons why this might vary within and across river basins is important for evaluating the risks for aquatic organisms and ecosystems. Co-occurrence across river basins suggests that even widely distributed species with large ranges could suffer substantial losses during co-occurring heat waves, while co-occurrence within river basins could be catastrophic for local populations because it implies that habitat areas with cooler temperatures might be absent or might not be accessible for those organisms. To measure whether heat waves co-occur, we first use the same algorithm as before to identify whether heat waves are occurring. In this schematic, we represent water temperature time series of those three locations in the black lines, and heat waves are indicated with the red shading. And then to measure whether they co-occur or are synchronized among locations, we can compare one location to another. We'll call these arbitrarily locations I and J using this metric S. And S is a measure of the number of days when there was a heat wave in both locations, divided by the number of days where there was a heat wave at either of the two sites. And this gives us a statistic that ranges from 0, where no heat wave days overlap, excuse me, to 1, where every heat wave day occurs at both sites. So perfect co-occurrence or perfect synchrony. And we can apply that in a pairwise fashion between site 1 and site 2, site 1 and site 3, and so on for all of the sites with suitable water temperature records. And for this analysis, we were not concerned about changes in time, but we wanted to include more locations in our analysis. So we loosened our time series length requirements and also added data from California from DWR's CDEC repository. And this about doubled the number of sites to 142. But as you can see here in this map of those sites, we have a lot more data in some regions and some river networks than we do in others. First, applying our synchrony statistic to all pairs of locations, a little over 10,000 pairs in total, we see that a modest amount of heatwave co-occurrence is common, with an average of 16% of heatwaves co-occurring between any parasites, but with much higher values approaching 100% co-occurrence, more rare, but possible. And that 16% might not seem like a lot, but one way we can help give context to whether that's meaningful is to compare how much co-occurrence we see in real life to a hypothetical case where we have the same number, the same duration of heat waves, but their timing is random. And when we do that, we find that for almost 90% of these location pairs, the degree of co-occurrence is well beyond what we would consider likely if heat waves occurred at random. Another way that we can visualize and begin to make sense of these data is by turning them into a network map, where the colored circles are study locations and links that are drawn between them identify pairs of sites where heat waves co-occur strongly. And I've also colored the circles based on a cluster analysis that identified groups of locations where heat waves have a high degree of co-occurrence with other sites in that group, but heat waves co-occur less frequently between sites in different groups. And it's notable, but not entirely surprising, that these clusters are really pretty geographically coherent. With limited exceptions, we have a set of slightly more southern interior locations, mainly in Colorado and Utah, that are grouped together. California is grouped together, and our Pacific Northwest and northern interior sites are grouped together. One reason this is an interesting map, though, is that there is pretty substantial co-occurrence of heat waves across different river basins within these regions, hinting that shared effects of regional climate could be playing an important role. And one way that we've explored this further is to break down the average rate of co-occurrence by year to see how it varies and to assess whether climatic conditions like temperature and drought explain those variations. We found that the average rate of heat wave co-occurrence across all site pairs varied from below 5% to more than a quarter um, from year to year, and that these fluctuations were explained reasonably well by the Pacific Decadal Oscillation, or PDO. PDO is a long-term climate oscillation. It has a period, as its name implies, around a decade. You can see peaks in about 2004, 2003, and then again in 2014, 2015, around there. Um, and in negative phases of the PDO, weather in the Western US tends to be cooler and drier, and in positive phases, weather tends to be hotter and wetter. And so we can see that heat waves tend to occur tend to co-occur at greater rates during warmer phases of the PDO, and possibly also in extreme dry phases as well. Another way that we can begin understanding the mechanisms that shape co-occurrence of riverine heat waves and their implications for water management is to zoom in on local river networks and ask how co-occurrence rates vary across these local networks according to the structure and features of the network. And there are several such networks in our data set, but for the purposes of this talk, I'm going to focus on what I think will be interesting to my California-centric audience, the Sacramento River. And these are brand new results. Not even my collaborators who've seen them before. And the reason that they're so new is that I just realized that some of the data existed. So data are available at different temporal resolutions, and it actually took me digging around for a different project to realize that many locations are reported at only one resolution or another, hourly or daily. And I was originally searching for daily data since that's the scale needed for these analyses, but that unknowingly excluded a bunch of places with only hourly data. So beginning to add to the story, first we have temperature time series and heat wave events for those 9 sites. And what will likely not be a surprise to folks in California water, we see high rates of heat wave co-occurrence in 2014 and 2015, and again in 2021, which are among our hottest and driest years on record. And now adding in a network map for this set of sites, where thicker lines connecting the sites correspond to a higher rate of co-occurrence. Two main things govern our expectations here. All else being equal, sites near each other are typically going to be exposed to more similar climatic conditions like air temperatures. And that water flows downstream. So a heat wave in one place will likely flow downstream unless some cooling takes place through some mechanism. And this is another way to visualize the rate of co-occurrence between pairs of sites, which helps us make some more observations. So this is a matrix that the x and y axes both indicate a site number, and you can see, for example, in the bottom left-hand corner, the bright yellow in the position corresponding to the rate of currents between Site 1, the Sacramento River just below Shasta Dam, and Site 2, the Sacramento River just below Keswick Dam. So some observations that we can make from this. So that site pair between Shasta and Keswick are highly synchronized. They're close, they're connected by flow, but our site number 3, which is Clear Creek below Whiskeytown Reservoir, is also close and behaves quite differently. So one of the things that this signals is, kind of the importance of, dams for disrupting heat waves. The potential for different strategies for dam management to disrupt heat waves. And indeed, if we kind of propagate this downstream and look at site number 4, which is at Red Bluff Diversion Dam, and compare that more modest degree of heat wave co-occurrence with sites 1 and site 2 are sites further upstream on the Sacramento River. Those inputs from Clear Creek appear to partly desynchronize heat waves in the upper Sacramento River. If you look at the other end of the system, our lowest sites, sites 8 and 9, are much more synchronized with higher Sacramento River, higher Sacramento River sites than the Feather River below Oroville, despite the shorter distances between them. And what this partly reflects, in all likelihood, is the greater discharge on an annual basis coming from the Sacramento River. Okay, so to give a quick wrap up of the science that I presented, here are a few takeaways. Heat waves occur in our streams and rivers, and they've done so with increased frequency over the past few decades. And this can have an important negative impact on aquatic life and aquatic ecosystems, and on the benefits that people derive from streams and rivers. And where and when heat waves occur is also influenced by large-scale climate and by local factors like river network structure and the positions and operations of reservoirs and dams. And that when heat waves co-occur synchronously, this can amplify their impacts. For example, because aquatic organisms have limited access to cooler refuge habitats. Although I describe these studies as more fundamental or curiosity-driven than work that's tailored towards specific applications or management recommendations, I do think they're pointing at some implications for water management. Recalling the negative impacts of aquatic heat waves for nature and people, opportunities to prevent them or to reduce their co-occurrence, assuming all else is equal, could prove important for maintaining diverse and functioning river ecosystems. We saw in the first part of this talk how heat waves tended to occur during periods of reduced discharge, so less water in the river. And this is partly controlled by our dam releases and water withdrawals, as well as fluctuations in large-scale climate. And at the same time, we saw that reservoirs can disrupt heat wave co-occurrence. And I think these facts are enough to pique interest in whether there are opportunities to manage water to prevent heat waves, and what would be the costs and potential co-benefits of such an approach. I'm not sure that I know enough about the water management side to speculate responsibly about specifically what that would look like, but I'm confident that with the right team that this is a solvable research problem. And of course, I also want to make a plug for the importance of data and data infrastructure for this work and for work like it. And by data infrastructure, I mean both the platforms for storing and sharing data and metadata, as well as the human resources. Um, Things like staffing to develop and maintain these platforms, training so that more people and organizations know how to document and share data effectively, and really to another important part of the human side of this is really just marshaling the cooperation of different people and organizations who naturally have different goals. It's really unfeasible for a single investigator or research group to make all of the observations that allow work like this to happen. And so without the will to share these data, the platforms for hosting it, adherence to standards for quality and formatting, appropriate documentation, all of these really kind of like technical and often boring things, work like this really can't happen, or would only happen at a glacial pace. So we do a lot of this already, but I also, know that there are opportunities to do better. Seemingly any time that this work comes up, somebody approaches me offering up a chunk of data that is not held in any public repository. And I don't say that to, shame any person. Data are really valuable. and the offer to share is really generous. But everybody's busy and is juggling other priorities. And so what we as a water data community can do to streamline that process and align incentives with having a more open and robust water data ecosystem. I believe that's going to yield new discoveries, more complete information, and in the end, the opportunity to make better decisions about how we manage water for people and for nature. Some of the work that I envision could give us some better information on river and heat waves, include how to quantify heat waves in shorter and discontinuous records. So earlier, I alluded to how the heat wave detection algorithm that we used was borrowed from studies of oceans, where their satellite-based data means that they have huge numbers of decades-long time series, essentially like wall-to-wall coverage. And in order to use those methods, we actually had to throw out a lot of shorter time series. For applications of streams and rivers, we could likely gain a lot by using statistical or AI models that borrow information about river temperatures from nearby sites, from atmospheric temperatures, and enable us to define heat wave thresholds for sites that have comparably less data, maybe as little as a few years. And this would allow us to quantify heat waves in a much larger number of locations and really make our understanding of how heat waves develop and propagate through river networks and impact the ecology much more robust. But at least to my knowledge, this hasn't yet been done. And researchers needed to be able to do it well and to understand the limits of what we can accurately infer with this approach. Another thing that's interesting to me is forecasting of heat waves and rivers. Traditionally, we sort of think of extreme events as being difficult to predict. But if we were to think about adaptive management of water infrastructure, it would be really exciting if we could forecast aquatic heat waves with sufficient time to to intervene, to do something different. Perhaps that's changing the configuration of Shasta Dam's temperature control device, or changing the rate of withdrawals from a stretch of river. I recognize that these are complex decisions that don't, necessarily hinge and shouldn't necessarily hinge on a single objective, like preventing an aquatic heat wave. My point is more that, research like this could produce useful tools for helping to make those decisions and understanding whether they're feasible. So with that, I'd just like to say thanks for listening. And yeah, now we're going to move toward a bit of discussion. And I hope that I've piqued your interest enough to stick around for that. Thank you.
Thank you so much, John. I'm going to start sharing my screen. We're going to actually move into the facilitated discussion portion of the agenda. We've been seeing a lot of questions come through the chat, so feel free to keep dropping those in. We have the informal discussion portion coming up after these facilitated discussion questions. We have about 3 questions for John that we prepared ahead of time. So let me share my screen. We can see those questions. Perfect. So John, as our climate continues to warm, how should we redefine what constitutes a heat wave? If warmer temperatures become the new normal, what are the implications for how we identify, measure, and respond to extreme temperature events in our waterways?
Yeah, this is a neat question. This is a thorny question too, in a way. So this is a case where there's pretty active discussion and research among people who study heat waves, because what we consider normal is changing, and what we consider normal is essential to identifying what's a heat wave. And the implication here is really that if we use a cooler past to define what's a heat wave now, and we know that the mean temperature has risen, then we're going to be biased toward detecting more heat waves. One way that we can guard against this having an outsized impact on our results is by constraining the reference period that we use to define what normal is. So a common standard for climate considerations is 30 years. And even though mean temperatures have warmed over that period, this is generally a fairly good balance between having a long enough period to not have an outsized influences of climate cycles like El Nino and PDO, while still being current enough to be representative. And in our studies, we're actually a little bit less than that, using the most recent 15 to 25 years. And there are also approaches to building trends into our quantitative definitions of what's normal that I think can be especially helpful when looking over long time horizons. Uh, Ultimately, though, I'm an ecologist. I'm interested in understanding the effects of heat waves on ecosystems and organisms. And often it's difficult to identify where those thresholds might be for responses to temperatures for a whole system, because they might vary from organism to organism. They might vary from process to process. If you want to think about sort of the biogeochemistry of these systems, things like ecosystem metabolism um, and that sort of thing. But in a perfect world, I think that might be a guide for us is understanding better how the ecology is responding and keeping those responses kind of at the forefront of how we define heat waves.
Thank you. Yeah, so it sounds like there's not one answer for this. It's always like kind of it depends, right?
Yeah, it's definitely an it depends story. And people make different researchers have made different choices about this. And I think in many respects, that's a good thing. I mentioned a little bit about very, very briefly, um, and this maybe foreshadows another question about threatened and endangered species. But there are species where we know that there are specific physiological thresholds. We know about their thermal responses, and if we want to tailor research, tailor policy, tailor management to those things, and there are often reasons for doing that, then focusing specifically on those thresholds is important too.
Yeah, that makes sense. I'm going to skip this question then since you kind of answered it and move on to the next question that we have. I think it's our final question. What would an ideal early warning system for riverine heat waves look like, and what data would it require?
Yeah. Well, so I think any good early warning system is going to give predictions that are accurate, and they're going to come early enough to enable some action. So I don't know that we yet have like a set of evidence-based practices to know exactly what early enough to take action means yet in this specific case. But I'm guessing that we're talking about at least a few days. Um, in terms of the data and what we would need, what kind of information we would need, it seems like at the very least we would need to know something about the current temperature at a location, what is coming from upstream, and have a meteorological forecast. And then, obviously knowing enough about what's been normal for a site in the relatively recent past to apply a heat wave definition. Is that short list enough? You might be interested to know that in the world of forecasting, there are problems, and this is like weather forecasting, where really detailed, physically based models work the best. And there are also other problems where stunningly simple models that barely seem to reflect any knowledge of how the system works actually produce good predictions. If I had to guess, this is a little bit more like the former. But if we can make good enough predictions from a reasonably simple model, that seems more likely to be useful.
Yeah, simpler the better, seems like. Okay, we've been getting a lot of questions in the chat, and I've been keeping record of them for John. So we have about 40 minutes, but we don't have to take the entire time. We typically don't necessarily have to fill this time, but I'm actually going to invite folks to come off mute and come off camera if they want to, after we kind of address some of the questions in the chat. So give me about 10 minutes while we go through these questions, and then I'll also invite people to um, come off camera if they want to have a chat with John. John, we got a couple questions, not a couple, a handful of questions. Colleen Cunningham asked, did you have any data for New Mexico?
Um, well, there are, um, I believe that there are data, I'm sure that there are data from Mexico, from New Mexico, excuse me, that just didn't fit our data inclusion criteria. Um, and which were relatively strict. And so, given what we were trying to do with the data and the requirements of the heat wave definition algorithm that we used, we were really, looking at, quite long periods of data. Again, like, 15 or more years, at least 25 in the case of the first study where we were interested in changes over time. And so that's um, probably many of you know this. Between the USGS, state and local agencies, right? We measure water temperatures in thousands of locations, and it's really the requirement that we have. These long and pretty continuous time series that caused us to, restrict that, data set down to, 70 to 140, depending on the study. And yeah, as I talked about kind of near the end, like that's something that I think we could relax using some different modeling approaches that borrow other kinds of information to essentially help to interpolate the missing data.
Yeah, that makes sense. Thank you for that. We have another question from Rebecca for John. I like the idea of using the potential for dam management to disrupt heat waves. It seems like most in-stream flow requirements encourage dam owners to release more in wet years. Is there an effort to change that to encourage dam owners to release more in hot, dry years instead?
Yeah, that's a good question. So I am not the greatest authority on what is kind of happening with proposals for dam management and water operations. This is an area that as I've kind of um, gotten my feet on the ground in California, I'm learning more and more about. Um, so I don't really have a good answer. For what's going on right now, I think this research and what other ecologists, fish biologists you know are saying is suggesting that those types of actions would probably be beneficial for the natural environment. But I think that we um, you know, want to be cautious about that because of the other important things that we use water for in these systems and um, the um, the possibility that if we did release too much water too quickly, then uh, and the sort of climate and meteorological conditions that gave rose favored heat waves and high river temperatures and low flows. If those were to persist in the future and we ran out of water, then that could also be catastrophic for nature and for people. And so I guess the answer is probably that there is probably some kind of optimum, right, where we can balance these different needs. I think the results that we have suggest that there could be some benefits that maybe haven't been been talked about and researched as much. But before making more specific recommendations, I'd really like to kind of investigate in more detail, kind of what the costs and benefits are, and think about you know the the fine details of strategies like that. Yeah. But I think it's a really cool question. Yeah.
Yeah, yeah, makes sense. Okay, next question from Ted. And also these are in the chat too if you want to take a look, and I'll make sure to send these to you, Jonathan, if you want to follow up with anyone offline.
Thank you.
So the way in which heat waves are measured as deviation from observed historical temperature patterns masks the way in which temp regimes are altered by dams. I wonder how your results would differ if you were to assess heat waves relative to natural temperature regimes rather than altered flow regimes.
Yes. So that's a really good question. And it's a very astute observation. For example, you might have noticed that sort of the degree to which the temperature immediately downstream um, of Shasta, it does not have nearly as much, sort of a, pronounced seasonal cycle to it. The amplitude of that cycle is, diminished a great bit compared to, even, say, I guess that's 60 or so kilometers downstream at Red Bluff. And so yes, the way that we've defined heat waves in this does not take that into account. It does show that those abnormally hot periods of time in river temperatures just below dams are tending to propagate downstream and have show co-occurrence with heat waves at downstream sites that are less strongly influenced by um, the dam releases themselves. Um, and because of that, depressed seasonal annual variation, if we were to, say, as you suggest, compare those temperatures to what the natural temperature regime would be. For that location if there were no dam there. I think we wouldn't see heat waves at all in those spots. And there are good there's a fair amount of work about whether that's a good thing for the biology. um, and most likely it is. I think there's research showing that it's not good because it's a different temperature regime than what the organisms that are adapted to living there are adapted to experience.
Yeah, thank you. Yeah, great question. Um, okay, next question. I think we have a couple more. One from Karen. Thank you for your interesting talk. Do you think that the Kendall test is the best method for modeling long time, daily, or monthly river data? Has your group considered any other methods such as state space models or GAMS? Any insight on the pros and cons of different methods for trend investigation would be greatly appreciated.
Yeah. Okay, this can get really wonky really fast. I'm a pretty big like time series modeling nerd. So I think it really depends on kind of what the question that you ultimately have is. For the kinds of trends that we were looking for in that first paper, the man Kendall was a pretty good choice. It's a, pretty common non-parametric test, and is reasonably conservative. And so it was a fair choice for what we were looking at with, sort of year over year trends. But as your data, kind of, and the questions of interest might become a little bit more nuanced, a little bit finer grained temporally. If you're thinking about, monthly or daily or even hourly 15-minute data. I know that type of stuff is certainly available with high frequency sensors. Then yeah, having approaches that account for those types of variation, whether that looks like sort of autoregressive models. State space is a kind of different question, because it's really getting at separating like your process from your model error. And that might be important for certain kinds of applications. There's also stuff in kind of the Fourier and wavelet world that can be really interesting, if you care about or you want to remove fluctuations that are on certain kind of timescales. So I guess the options are vast, and I'm gonna uh, you know stop commenting there before I just, name a list of methods that are cool. So
Yeah, thank you. And Karen, if you want to follow up with John offline, well, we can share his email in the chat as well.
yeah, yeah, please feel free.
Next question from Carrie. John, where did you heat wave measure for Mill Creek? It has such a small volume of water. Why was it studied? Why not Deer Creek?
Um, just happens to be where I found data. So in in these studies, the only criteria that I chose was being able to find a time series that met our criteria for inclusion in the study. Beyond that, there was no other attempt to, kind of focus in on, particular sites or particular streams. Um, certainly, I'm sure that there are temperature records on Deer Creek that we could find, and potentially find a way to to use that data to investigate what's happening there too.
That makes sense. I'm replying to some folks in the chat to see if they'd like to come off mute and ask their questions directly to you, while I keep going through the chat here for you, John. Lu Han asks, the heat wave synchrony is defined as heat waves that happened at the same time. What about the heat wave at different locations that have a few days of lag? These could be the same heat wave that propagate downstream, more driven by river flow than local climate.
Yeah, that's a good point. And we didn't try to account for lags in this study. That's something that we may be able to do in future work. Um, yeah, so that's a good question. And that's something that, certainly, we think is happening. Um, I will say that, because our, heat wave algorithm, uh, you know, uh, has a, 5-day definition for a heat wave to occur, that, depending on certainly the flow rates through a system, it might have to be a pretty long distance away for um, that measure to pick up, no co-occurrence, excuse me, no co-occurrence whatsoever. But it's a good question, certainly overall. Yeah, thanks.
Awesome. I'm going to ask Albert to unmute. He's going to ask your question directly, and let me just make sure that the Zoom controls are enabled. You should have access there, Albert.
Hi, Jen. Great work. Really interesting results. I was wondering about the synchrony aspect. I think, if I understand correctly, synchrony in the occurrence of events. And I was wondering, have you attempted to see synchrony in amplitude to try parse out, like really severe heat waves from relatively minor ones? I wonder, like, if wavelets or, these things could help. But in any case, it's very interesting work. So thank you.
Yeah, thank you. Yeah, Albert, that's a good question too. And it's not something that we've looked at yet. Um, yeah, so again, like I think it's a really cool question, and one where, yeah, we don't really have, haven't have some work yet. And just thinking a little bit about the question, I can almost imagine there being a couple of different, possibilities that could go, different directions. One might be that, these sort of, really extreme events are so, just like they're extreme, but they're also widespread, right? If we see, a large drought, a large atmospheric heat wave that drives dynamics over large areas, many different river basins, that they could be more likely to be synchronized. On the other hand, it's also sort of possible that a really severe, heat wave is sort of a perfect storm of rare events, and that, kind of those rare events are somewhat idiosyncratic to a location, and they might not be as synchronous. But yeah, it's a cool idea, a cool set of thoughts. So thanks for that question and the suggestion.
Thank you.
Awesome. Next question we have from Ted. I don't know, Ted, if you want to come off mute and ask the question directly. Otherwise, I can read it for you. Oh,
Yeah. Can you hear me?
Mhm.
yes.
Yeah, no, I was reflecting on some of your slide where you're talking about maybe future areas of research, and I was just curious if you thought kind of looking into sort of attribution of heat waves, and I'm particularly curious if like you have the data or thought about how you might separate the influence and quantify the influence of sort of hydrological versus atmospheric kind of factors that are contributing to heat waves.
Yeah. I mean, one way to go about that might be, is sort of like a simple kind of heat budget model, where you have, sort of like what's flowing in to the system, um, as well as, terms for, the atmospheric heat exchange and, terms for solar radiation. And, there's some other terms that you might want to, include too to kind of close the loop on stuff. But that might be a really good, I would think that that might be a really good starting place in terms of, kind of understanding the range of what's possible, physically, and then, kind of trying to, confront those expectations with data, and see how closely the patterns that we see in the model, might match. And there are probably some places that, that we can do this with the data that we have already. We have stream temperatures, we have, discharge, and if we have a relatively simple stretch of river, then that's probably a really good candidate for, um, being able to, investigate that, kind of stuff with data. But I think having a physical model too would also be really helpful. And as kind of brought up, kind of doing the attribution part.
Thank you so much and great talk.
Yeah, thanks so much. Thanks for the question.
Awesome. And we have one more question in the chat. And again, if anyone feels like they want to, pose their question to John directly, feel free to raise your hand or drop it in the chat. I can read those off. A question from Shahariyar. I'm sorry if I messed your name up. Shahariyar. This research is valuable because it uses a large data set to clearly show how heat waves in U.S. rivers and streams are becoming more frequent, providing important information for addressing the impacts of climate change on these vital ecosystems. But how can we develop predictive models to forecast river heat waves and inform management decisions?
Yeah. Well, first, thank you for the really positive feedback in the first part of that question. I appreciate that a lot. Yeah, so the second part, getting at, how we can, we can do this. I think that there are some interesting, well, there's work to build on, modeling, modeling river temperatures. In my response to to Ted's question previously, I mentioned some of those kind of heat budget type of models. One way, and kind of a way that I've been imagining doing this for the most part is making something that is at least sort of partly physics based. Maybe it has some fudge factors in it to help the or some free parameters in it to kind of help the model fit the data a bit. But having something that is at least partly physics based and really focus actually on modeling the river temperature itself, and then sort of overlaying our heat wave definition on top of it. And there's a rich and enormous literature on different approaches to modeling river temperatures that range from really mechanistic approaches to strictly empirical ones and things that are kind of in between that have kind of statistical or machine learning models that whose structure is informed by some notion of the physics behind what heats water and cools it down. And all of that stuff gives a really good platform to work on. But it might also be interesting to kind of take a different approach that's a little bit more that doesn't rely on directly modeling river temperatures themselves, but instead focuses on trying to build a model of of the heat wave as as an entity in and of itself. I'm not sure if that would be as as profitable and as useful for for management. Maybe it would, maybe it wouldn't. But yeah, that's a different strategy, and I think both of them would be interesting to to investigate.
Awesome. So it doesn't look like we have any other questions in the chat. So I'm going to go ahead and close us out. Thank you again, Jonathan, for your time today and your amazing research. I dropped some links in the chat for folks. Please don't forget to complete your survey and register for those events that I mentioned. Thank you all for joining our April Data for Lunch.